In 1953, the astronomer Fred Hoyle had a problem. He was studying how stars make different elements in their cores, and he realized that there's much more carbon in the universe than there should be. Stars fuse hydrogen into helium and then helium into beryllium-8. That part is chill. But to get carbon, you need to fuse 3 helium nuclei together. But beryllium-8 is really unstable. It falls apart in about 10 to the negative 16th of a second. That's 1/10 quadrillionth of a second. So the third helium nucleus has to fuse with the beryllium in that fraction of a second, and when you run the numbers, the reaction is far too slow. So according to nuclear physics, stars should make almost no carbon. But clearly they do. Carbon is the 4th most abundant element in the universe. You and I are made out of carbon. Hoyle knew that we were missing something, and predicted that there had to be an excited energy state, a resonance, sitting near 7.68 mega electron volts, which would vastly increase the chances of 3 helium nuclei coming together to fuse into carbon. He was visiting Caltech at the time, and he asked his experimentalist colleagues to look for this resonance. And they found it at 7.65 mega electron volts, 0.5% off from Hoyle's prediction. It is now known as the Hoyle resonance. And if we shift the Hoyle resonance up by just a few percent, stars make essentially no carbon. Shift it down by a similar amount, and they make carbon, but barely any oxygen. It's like the dial is set to exactly where it needs to be to produce both carbon and oxygen, which are so essential for life.
What people don't realize is that the lack of a resonance in oxygen stops all of that carbon being converted into oxygen. There's this balance between a resonance occurring in carbon and a lack of a resonance in oxygen means that we've built up that useful carbon atom in the universe.
And when you look closely at the laws of physics, you keep finding numbers that look dialed in, values where a small change would mean no chemistry, no complexity, no stars or galaxies, or us. It's weird. It turns up in so many places, and the explanations are, well, we'll get to that. When you look at the laws of physics, there are the equations, and in those equations, there are constants, like this is Newtonian gravity, and this is the general theory of relativity, and they predict how things fall to the ground, how planets move around the sun, etc., etc., except that they don't. Not without this constant.
Throughout all of our laws of physics are these numbers, right? The fundamental constants. And the thing is that the mathematics of physics is sterile until you know those constants. And the only way that we get those constants is by asking nature. So I could give you Newton's law of gravitation, right? But there's no way you can calculate the orbit of the moon, how long it's going to take, etc., until you know how big G is.
The big G in these equations is the strength of gravity, the universal gravitational constant. In our universe, it's around 6.674 times 10 to the negative 11 meters cubed per kilogram per second squared. And you can't get this number from the theory. It's not something that can be derived. It had to be measured, which Henry Cavendish first did in 1798. He suspended 2 small lead spheres from a torsion wire inside of a sealed shed and watched the wire twist as 2 350-pound lead balls pulled the small spheres towards them. The force he was measuring was about the weight of a dust speck, so the signal was so faint that he had to watch it through a telescope from outside the shed, because his own body heat would have stirred up the air so much and swamped the signal from gravity. And by measuring how much the wire twisted, he was able to figure out the strength of gravity. There's an amazing video about this experiment by Steve Mould, by the way. If you haven't seen it, you really should. Hey, you might have noticed something. Units. The meters, the seconds, the kilograms, they're all human inventions and are arbitrary. And you're right. But what isn't arbitrary are the ratios between the constants. The mass of a proton and the mass of an electron are also constants that we had to measure, and a proton has a mass that's 1,836 times greater than that of an electron, and it doesn't matter what units you are measuring in.
And of course, the actual value depends on the units that you use, but you can express combinations of constants in dimensionless ways.
So there are about 30 of these constants, these dials. They aren't set by any of our theories, so in theory, they could be different numbers. So the obvious question is, what if they were different numbers? What happens when you start turning these dials? So let's turn some dials. In our universe, neutrons are heavier than protons by 1.29 MeV, which is about 0.14% of a neutron's mass, or 2.5 electron masses. The difference in their mass is tiny. In our universe, a free neutron can decay into a proton, but a free proton is stable. And this is really important, because if a proton was heavier than the neutron, the proton would decay into neutrons. This means hydrogen atoms would decay. Protons would capture their electrons and turn into neutrons. A universe without even hydrogen, let alone the rest of the periodic table, is likely very, very boring. Just endless neutrons doing basically nothing. Another dial that we can mess with is the strength of the strong force, the fundamental force that keeps atoms together. The first step in the chain that powers the sun is fusing 2 protons into deuterium. Deuterium is bound by just 2.2 mega electron volts. It's barely holding on. Weaken the strong force by just a few percent and deuterium falls apart, and the fusion chain never gets started. Fusion does not get started. The thing that makes stars, stars. The stars that make every element of the periodic table inside them. The stars that burn out and scatter their heavy elements across the universe. The stardust that we're made of. Those stars. If the strong force was just a few percent weaker, we'd have no stars.
And what you rapidly find is that it's easy to kill a universe. And what I mean by that is you can end up with universes that are definitely not going to be habitable. You rob them of the key thing that we think is important about life, and that's complexity to encode information, all this kind of stuff. The question then turns to is then, okay, we appeared to live in a universe where we've got constants that allow us to be here. And is that telling us something? Is there something underlying about the nature of the universe? Because we live in a universe that seems to be in some sense special.
We can also mess with gravity. Compared to the other fundamental forces, gravity is pathetically weak, which is why a fridge magnet can beat out the pull of an entire planet. The electric repulsion between 2 protons in a nucleus is about 10 to the 36. That's a trillion times stronger than the gravitational pull between them. So why is gravity so weak compared to the other forces? Well, we don't know. But if we make it 1,000,000 times stronger, I know that sounds like a lot, but now it's 10 to the 30 instead of 10 to the 36, is still so much weaker than the other forces. Well, in that universe, stars will live for about 10,000 years and not 10 billion. Likely not enough time for complexity or life to arise. Okay, let's just mess with one more constant. Please indulge me. In 1929, Edwin Hubble discovered that the universe was expanding. But we have stuff in this universe, and the stuff being acted upon by gravity should be getting pulled in. So the thinking was that the faraway galaxies flying away from us should be slowing down. But measuring this is really tricky. It took another 70 years for us to find this answer. Here's how we did it. In our universe, we have this particular kind of supernova called a type 1a supernova, which occurs when a white dwarf sucks in the matter from another star that it's orbiting next to. And at a certain point, around 1.44 solar masses, known as the Chandrasekhar limit, the electron degeneracy pressure that's keeping the whole structure up gives out. The details are interesting and complex as usual, and I'll get to it in another video, but what matters here is that these stars explode at basically the same brightness, so you can use them as standard candles. This is what astronomers call them. And the brightness of an object follows the inverse square law. A candle that is twice as far away is only a quarter as bright. So if you know how bright the thing that you're measuring actually is compared to what you measure it to be, you can figure out the distance. And you can measure how fast something is moving away from you by seeing how the light is redshifted. The light waves that are moving away from you faster get stretched out more. In the late 1990s, two teams, the Supernova Cosmology project, led by Sol Perlmutter out of Berkeley, and the High-Z Supernova Search team, led by Brian Schmidt out of Canberra, were using this method to measure the rate of the expansion of the universe. But Type 1a supernovae are rare, so how did they find them? Well, they photographed thousands of galaxies, and then they came back weeks later, photographed them all again, and had a computer subtract one image from the other. If you see a new bright spot appear, it might be a 1a supernova. And the results they got were very surprising. So surprising that they thought they made a mistake. The rate of expansion of the universe wasn't slowing down. It was speeding up. The cosmological constant was positive. There is something that is pushing the universe apart, not just counteracting the pull of gravity, but overpowering it. We now call it dark energy, and we're still not sure what it is. In 2011, Perlmutter, Schmidt, and Rees won the Nobel Prize. But the history of the cosmological constant goes back more than 100 years. Back in 1917, Einstein had a problem. His own equations insisted that the universe should be expanding or contracting, but everyone knew that it had to be static and eternal. So he added a term to the equations by hand, a kind of anti-gravity built into space itself, tuned precisely to hold everything still, the cosmological constant. Hey, quick side note, there's a story that people say that Einstein referred to his edition of the cosmological constant as his biggest blunder, and we actually don't have first-hand sources of him saying that. There is a book by George Gamow from 1970 and an article from 1956, and also maybe a couple of other scientists, a couple of other physicists that have heard him say something like that. We don't know if he called it his biggest blunder, but we do know that he hated it. In a letter to Georges Lemaitre, he wrote, "Since I had introduced this lambda term, I had always a bad conscience. I had found it very ugly indeed that the field law of gravitation should be composed of two logically independent terms, which are connected by addition. I cannot help to feel it strongly, and I am unable to believe that such an ugly thing should be realized in nature." Which is a shame for Einstein, because such an ugly thing is realized in nature. The cosmological constant exists, and it seems fine-tuned. Anyway, dark energy, what could it be? Well, there's an obvious candidate. Empty space isn't truly empty. Take a box, get rid of every atom, every particle, and then cool it to absolute zero. Quantum field theory says that vacuum is still not empty. There are virtual particles and antiparticles popping up, buzzing with energy. Exactly the kind of thing that could potentially push space apart.
So we know that there is this underlying field of energy in the universe, which over the last 5 billion years has come to dominate and is driving the expansion of the universe faster and faster. So this dark energy discovered at the end of the 90s. And when you do your calculation of quantum field theory about how much dark energy you expect, the amount that we have is a teeny sliver compared to what there could be. Right? It's 1 part in 10 to the 120, some ridiculous number.
The theory predicts that the vacuum energy of empty space should be 10 to the 120 times bigger than what we measure in our universe. If dark energy is the energy of empty space, which would make sense, we're off by a factor of 10 to the 120. It has been called the worst prediction in the history of physics. But this dark energy is also fine-tuned, 100 times more than what we measure in our universe, and galaxies don't form, or only very small ones.
And you can rapidly see that if you make it too large, then the universe would be born, and then all the matter in the universe would be spread out such that it would be completely diluted, that you'd never form stars, never form galaxies, etc. So you could potentially wind the amount of dark energy up by a factor of, let's say, 100. Okay? Now you might say, oh, 100? That sounds huge, right? A factor of 100 larger. But a factor of 100 in 10 to the power of 120 is still next to nothing, right? It's a small volume. So there is a little bit of give in there, but compared to the potential range, right, there, it's tiny. So instead of a big galaxy like the Milky Way that you have today, you end up with these small, compact little blobs of galaxies. And they are not good places for life, because you get supernova in there, you get black holes in there, you get all kinds of stuff going on in a small volume, which, is part of the reason why the center of our Milky Way is not a good place for life. It's too much going on in too small a volume. So I say a factor of 100, but the volume is probably smaller than that.
One of the things that I find wild here is that Steven Weinberg predicted a positive cosmological constant back in 1987, a decade before we had the measurement of it. He reasoned that because we exist and that galaxies are pretty big, we must live in a universe where there's a small but non-zero amount of dark energy, a few times more than the density of matter, which is about what we measured. I find this paper to be remarkable because it uses the fact that we exist to make a prediction about the universe. Weinberg's prediction is based on the existence of us and of galaxies, and so the value of the cosmological constant must be low enough for galaxies to form. And this prediction ended up being basically right. I mean, how cool is that? But it's not just the constants of nature that allow for complexity to arise. We can mess with some other knobs too, for example, the initial conditions. Our universe started in a very, very low entropy state. This is the whole second law of thermodynamics thing, that over time entropy goes up, things spread out, they become mixed. This is why we have the arrow of time. Another way of saying low entropy is saying high available energy, the ability to do complex, interesting stuff. If the universe was born in this high entropy state, you don't get complexity. Why is the initial state, why are the initial conditions of the universe such a low entropy state? Why was it this way? This is super weird.
Our universe was born in a state where matter was smoothly distributed, so it had the potential to collapse and clump together into stars and then into galaxies. So it was born in a low entropy state. It was born with lots of possible energy. But if the universe had been born instead with all of the matter clumped together and locked into black holes, well, all of that gravitational energy is gone, right? You can't do anything really with black holes. You can bring them together, but what are you going to do with that? One of the things that we take for granted is the entire existence of the arrow of time. Why does time point in one direction? It doesn't have to. There is nothing in the equations of relativity that tells you which direction time should run in. Can you imagine physics if we had time running in both directions? That is possibly one of the biggest fine-tuning.
Also, the dimensions that we live in, 3 dimensions of space and 1 of time, are conducive to complexity. In 2, everything's really boring, and in 4, well, orbits don't really work. And I can't even imagine what 2 dimensions of time would look like, let alone more.
I mean, why 3 dimensions of space and 1 of time? There's nothing in the equations of relativity that says I can't add another minus dt squared term. I can add as many as I want, and I can do all my laws of physics. But what does that mean if you were a being in that universe with multiple dimensions of time? Right? So I can play these games, But if I want to then talk about habitability in those universes, then I've got to talk about how the laws of physics behave in those universes.
So how should we think about all of this? Well, to some degree, this is obvious, right? We're here because we're here. Out of all of the possible universes, with all of the possible settings of the dials, the only ones that ever get noticed are the ones where the dials let observers exist and do the noticing. A universe with no stars, no chemistry, no brains, has nobody in it to marvel at how dead it is. Douglas Adams, the author of Hitchhiker's Guide, wrote about the sentient puddle, where after some rain, a puddle forms, gains sentience, and thinks to itself, "This is an interesting world I find myself in. An interesting hole I find myself in. Fits me rather neatly, doesn't it? In fact, it fits me staggeringly well. Must have been made to have me in it." So maybe it's as simple as that. Maybe it's just we're here, and that's it. And stop asking questions. And that just doesn't feel satisfying to me. It doesn't feel scientific. Throughout the whole history of science, the stop asking questions, things are the way they are, that approach hasn't been very successful. Being painfully, annoyingly curious has been. So maybe there's a deeper theory of physics that we're missing that explains why the constants are the way they are, why the initial conditions are the way they are, that explains the 3 dimensions of space and 1 of time, etc., etc. And that would be really cool, but it does just push fine-tuning to another level.
You go, look, physics is done. There is no freedom. These are the ways that the fundamental constants are. And you say, right, job done. Except your job isn't done.
Why?
Because the library of possible mathematics is infinite. And the mathematics used by this universe is a slim volume in an infinite library. Why did our universe choose that set of mathematics to describe the universe?
Or maybe a way to explain all of this is theological. If there are all these parameters, all of these knobs that seem so fine-tuned for life, maybe there's a fine-tuner, a creator that made this universe just so perfect for us.
So let me just explain the context of the book, right? So it's written by myself and Luke Barnes. So I am an atheist, Luke is a theist. And we have seen this argument from both sides. For Luke, he sees plenty of people saying that fine-tuning is evidence of a creator. For me, who doesn't have that particular hypothesis, that this is evidence for something deeper going on with the nature of the universe. For me, the notion that saying if we just do more physics, we'll solve it, I don't think we do. I think we just move fine-tuning elsewhere. So for me, the thing that helps me sleep at night is the notion of the multiverse, right?
That there is an unfathomably large collection of other universes where the constants of nature and the initial conditions and maybe even the mathematical structures are different. Some small percentage of them allow for complexity and for life, but most don't. And we're one of the lucky ones. We live in a fortunate universe.
We have to let science play out. What we shouldn't do is let noisy people shut down the debate because they don't like a concept, right? And
I love this.
I've seen plenty of people say, should not talk about the multiverse. That's not the way science works. Science is playing out and we are not at the end game.
And a lot of smart people fall into these different camps. Hoyle, for example, said, a common sense interpretation of the facts suggests that a super intellect has monkeyed with physics. Martin Rees looks at the same data, and this pushes him towards the multiverse hypothesis. I don't know what to make of this. It's why this tab has been open in my brain for a decade. I don't even know how seriously to take it. Personally, I lean towards the multiverse argument because there is a lot of good reasons to take the multiverse hypothesis seriously that's independent of fine-tuning. But I just don't know. I genuinely don't know what to do with this information. I just think it's interesting and really neat and very weird. When I worked at Veritasium, we really tried to tell stories that had a clear beginning, middle, and end. The setup, the building tension, and then the resolution. Something that put a nice, neat little bow on the video. There is no bow on this video. I want to say that I'm sorry that I'm not giving you a resolution here, but I'm just not. Humanity does not know the resolutions to some massive, fascinating, consequential problems. As John Wheeler famously said, as the island of knowledge grows, so does the shoreline of ignorance. When we learn things about the universe, we end up getting more and more questions to ask, more mysteries to unlock. That's lovely. That's how science works. And I like that I've had this problem in my brain for a decade. I like that this tab is open in my brain. I also like that this is an advanced question to ask. This feels like a tremendous success of science to get to the point where we are rudely slapped in the face of how fortunate our universe seems to be, and how strange that is. I love being reminded of our insignificance and of our fortune. If you want to learn more about cosmological fine-tuning, you just have to read Geraint and Luke's book. It's really, really approachable, and it's beautifully written. It's really, really good. As always, the reference list is in the description, including a few books that I'd recommend on the topic. And if you have a well-paying job and you find the stuff that I make to be valuable, I would really appreciate it if you could subscribe to my Patreon. Thank you for being here. I'm grateful to share this fortunate universe with you.